Welcome back to the deep dive. We're here to take complex source material and, well, make it stick, make it useful knowledge you can apply right away.
Exactly.
Today, we are really getting into something absolutely non-negotiable for operating a high-performance turboprop like the King Air 350.
Mm-hmm.
Ice. Specifically, how to manage in-flight icing. We're treating the aircraft's complete ice and rain protection suite, not just as a bunch of switches, right, but as this holistic system.
It has to be seen that way. It's essential for survival, frankly, and just basic professionalism in the cockpit.
And we need to stress the seriousness from the get-go, don't we?
Well, we absolutely do.
Okay.
Look, the King Air 350, it's certified for flight in icing conditions as defined in FR 25 Appendix C. That's the standard.
Right.
But, and this is a big but, the training materials, the POH, they explicitly warn you certain conditions, things like freezing rain, freezing drizzle, or maybe severe mixed conditions.
Stuff that isn't perfectly defined in Appendix C.
Exactly. Those conditions can create ice accretion rates so fast they simply exceed what the aircraft systems were certified to handle.
And then you're outside the safe envelope.
You are operating in uncharted territory, essentially. So understanding these systems inside and out, how they work, their limits, that's the only way to recognize those conditions and know when to, well, get out.
Okay, so let's treat this deep dive as exactly that. Your comprehensive audio study guide. We're going beyond just flip this switch. We need the why, the engineering behind it.
Yeah, the rationale. It's a mix of systems, isn't it? You've got pneumatic, you've got electrothermal, even exhaust heat being used. They all have to work together.
Okay, so the roadmap. What are we covering specifically?
Right, let's lay it out. We've got 5 main areas to cover for managing ice and rain. First, the big one. The airframe de-ice, those pneumatic boots.
On the wings and tail.
Correct. Then second, we'll look at the propellers. Third, keeping the view clear. Windshield anti-ice and the wipers.
2 separate things there.
2 separate things, yeah. Fourth, absolutely crucial, engine ice protection for those PT6As.
Can't fly without them.
You certainly can't. And finally, number 5, the smaller bits that are easy to forget but vital. The probe and sensor heating systems.
Pitot tubes, stall warning, that kind of thing?
Precisely. Covers everything.
All right, let's start with the largest surfaces then. The wings and the horizontal stabilizer. Protected by pneumatic boots. Now, the terminology here, you mentioned this, it's critical. This is de-icing, correct? Not anti-icing.
That's the fundamental distinction, yes. De-icing.
So what's the operational difference? Why does that matter so much?
It's everything, really.
Yeah.
Anti-icing, like windshield heat, aims to prevent ice from forming in the first place. De-icing, like these boots, is designed to remove ice after it has already formed.
So they're reactive.
They are reactive.
Yeah.
The whole principle is they inflate, they literally crack the accumulated ice layer, and then the slipstream, the airflow over the wing, sheds that cracked ice.
Okay, reactive. So that means, critically, the pilot has to wait for some ice to build up first.
Correct. You must wait for accumulation. You can't just turn them on the second you see a cloud.
So what's the guideline then? How much ice are we waiting for before we hit that switch?
The standard recommendation, which you'll find in most operator procedures, is to wait until you visually observe about 1/2 inch to maybe 1 full inch of ice accumulation.
1/2 inch to 1 inch. Where are you looking? On the boots themselves?
You can look at the boots, yeah, or any other unheated part of the airframe that's visible from the cockpit, like the wing root area, maybe an antenna, something like that. Gives you a gauge.
Okay. And why not just cycle them sooner? Keep the ice thinner?
That's where we get into a really critical concept. Something called ice bridging.
Ice bridging. Right. This sounds important. Let's nail this down. What is it exactly?
Okay, so imagine you activate the boots too early. The ice layer is still very thin, maybe 1/4 inch, and it's still relatively pliable, not fully brittle yet. When the boot inflates underneath that thin, flexible layer, instead of shattering the ice, the rubber just pushes it outwards, creating sort of a hollow space, a cavity underneath the ice.
Okay, I can picture that.
Then when the boot deflates, the ice, which is still bonded pretty well at the edges, just settles back down. But now it has this air gap trapped inside it.
Oh, and that gap.
That gap can then fill with moisture or simply refreeze solid over time, forming this rigid, thicker shell of ice that is effectively bridged over the area where the boot inflates.
Making the boot useless.
Completely useless for the next cycle. The pneumatic pressure simply can't break through that now much thicker, stronger, bridged ice structure. You've actually trapped the ice, you've ensured it's going to keep accumulating, and worse, you've created a really nasty, unpredictable shape on your leading edge.
Which ruins the airfoil's lift.
Exactly. Ruins lift, increases drag, can significantly alter stall characteristics. This is why that patience, waiting for the half to 1 inch, is so critical. You need the ice brittle enough to shatter, not flex.
Okay, message received. Wait for the accumulation.
Yeah.
Now, assuming we've got our half inch or so, how does the system actually inflate these boots? Where does the pressure come from?
It uses engine bleed air. High-pressure air tapped directly from the compressor section of each engine.
Okay.
That air is regulated, of course, and it passes through firewall shutoff valves. That's important for safety. Means you can isolate the system in case of an engine fire or other emergency.
Right. And the control in the cockpit?
It's the surface D switch. Key thing here is it's spring-loaded back to the OFF position.
So you can't accidentally leave it inflating continuously.
Precisely. Prevents that.
Okay, talk me through the modes. There's a single cycle mode.
Yes. If you just momentarily move that switch to single and then let it spring back to OFF, you trigger one complete automatic cycle.
What happens in that cycle?
It's timed and sequenced. A distributor valve directs the bleed air first to the wing boots. They inflate for about 6 seconds.
6 seconds for the wings?
Then once the wing inflation is done, the valve redirects the air and the tail boots on the horizontal stabilizer inflate for about 4 seconds.
Interesting. Wings first, then tail. And different durations. Why sequence it like that? Why not just inflate everything at once? Save time.
Good question. There are a couple of reasons, mainly aerodynamic and managing the load. First, inflating everything at once creates a pretty significant, albeit momentary, drag increase. Sequencing smooths that out a bit.
Okay.
But perhaps more importantly, especially on an aircraft like the King Air, if you shed a large amount of ice from both the wings and the tail simultaneously, you could potentially get a sudden, kind of unpredictable shift in the aircraft's pitch moment or center of lift.
Could upset the handling?
Could definitely unsettle the aircraft momentarily. Sequencing the shedding wings first, then tail makes that process much smoother and more predictable for the pilot.
Got it. Okay, that's single. What about the manual mode?
Manual is different. If you hold the switch over the manual position, and you have to physically hold it there against the spring, all the boots, wings, and tail inflate together and stay inflated for as long as you hold that switch.
When would you use that?
Mostly for maintenance checks on the ground, to verify inflation. In flight, maybe if you suspected the automatic timer had failed, but it's not the normal operational mode. You let go, it springs back to OF, and everything deflates.
Okay, so inflation uses bleed air. But once the cycle's done, or when the system is off, we need those boots held down tight against the wing, right? Not flapping around.
Absolutely critical for aerodynamics. You can't have them loose.
So how does it achieve that? How does it deflate them and keep them snug?
That's actually a separate pneumatic system, using a vacuum. It's quite clever. It uses a Venturi ejector.
A Venturia, like in a carburetor.
Similar principle. It uses a small, dedicated flow of engine bleed air forced through a narrowed section, a throat. As the air speeds up through that throat, the pressure drops dramatically. That's Bernoulli's principle, creating suction, or vacuum.
Okay.
That suction is then piped to the de-ice boots, pulling the rubber tight against the leading-edge surfaces when they're not being inflated.
So, wait, the system is using bleed air even when the boots are off, just to maintain that vacuum?
That's exactly right. It's a continuous process when the engines are running. That vacuum system is always working, ensuring the boots maintain the proper aerodynamic shape of the airfoil. No flapping, no extra drag, no weird handling characteristics.
Huh. Clever. Okay, indications in the cockpit. How do I know a cycle is actually running when I hit single?
You'll see the wing dice and tail dice annunciator lights come on.
Okay.
But here's the key thing to remember about those lights. They only illuminate during the actual inflation period for each section. So wing dice comes on for about 6 seconds, then goes off. Then tail dice comes on for about 4 seconds, then goes off.
So they're not fault lights, they're just showing pressure is being applied now.
Exactly. They confirm valve operation and pressure application for that specific segment. They are action indicators, not fault indicators.
How do you monitor the overall health of the system then?
You watch the pneumatic vacuum gauge. That's your main system health indicator.
What are you looking for on that gauge?
Well, during an inflation cycle, you watch the pneumatic pressure needle. It should rise and stabilize somewhere in the green arc, which is typically between 12 and 20 psi.
And 20 psi is the limit.
20 psi is the maximum operating limit. You don't want to exceed that. When the system is off or between cycles, you should see the needle indicating vacuum pressure, confirming that Venturi ejector is doing its job holding the boots down. Fluctuations on that gauge during cycles are normal.
Okay. And one last critical point for the boots themselves. the temperature limit.
Yes, this is a hard limitation in the AFM. You must not operate the de-ice boots if the outside air temperature is below -40 degrees Fahrenheit.
Which is also -40 Celsius, conveniently.
Exactly. -40 is -40. The reason is structural integrity. Below that temperature, the rubber material of the boots can become extremely brittle.
And inflating them could crack or shatter them.
Precisely. Could cause permanent damage, rendering them useless. So, extremely cold temperatures, below -40, no boot operation.
Okay, let's shift gears now from the pneumatic boots on the airframe to the propellers. Different system entirely, right? This is electrothermal.
Correct. We're moving to electrical heating elements now, specifically for the propeller blades. Primarily a de-icing function, but the heat is very localized to prevent big chunks forming.
Where are these heating elements located?
They are embedded as boots right onto the leading edge of each propeller blade, usually near the root, extending partway out. They also cover the area around the pitch change mechanism.
And how does the pilot control the heat? Is it just ONOFF?
Not quite. The pilot selects the automatic prop de-ice switch to the on-end position, but the system itself doesn't apply heat continuously. That would be bad for the blades.
Why bad?
Think about it. A propeller spinning at high RPM, applying constant uneven heat could lead to thermal stress in the blade material, potentially causing delamination, especially in composite blades. And critically, uneven heating or shedding could cause an imbalance.
Ugh, vibrations. Serious ones.
Very serious. So to avoid that, the system uses a very precise internal automatic timer.
Okay, a timer. What does it do?
When you select all-UDO on-end, this timer takes over and sequentially cycles electrical power to different pairs of propeller blade elements across both propellers. It might heat, say, blades 1 and 3 on the left prop and 2 and 4 on the right prop for a set period, then switch to the other pairs.
Ensuring even heating and shedding across the prop desk.
Exactly. Even thermal distribution, balanced ice shedding, minimal risk of inducing vibration, it's all carefully timed.
So if the system is handling the timing automatically, what's the pilot's main job here? Just turn it on and forget it?
No, definitely not forget it. The pilot's primary role becomes monitoring. You turn it on, but then you must confirm that the automatic timer is actually working correctly and that the heating elements are drawing the right amount of electrical current.
How do you confirm that?
Through the dedicated de-isometer. That's your window into the system's health. The procedures, especially during pre-takeoff checks on the ground, specifically require you to monitor that ammeter for at least one full timing cycle.
How long is a cycle usually?
The ground check procedure specifies monitoring for 90 seconds to observe the cycling.
Okay, 90 seconds. And what should I be seeing on that de-isometer during a normal automatic cycle?
You're looking for the needle to be indicating within the marked green arc on the gauge. That range is typically 26 to 32 amps.
26 to 32 amps. Stable.
Mostly stable within that range.
Yeah.
You might see a very brief flicker or dip in the needle as the timer switches power from one set of elements to the next. That's normal. But otherwise, it should hold steady within that green arc.
What if it's outside that range? Below 26?
A reading consistently below 26 amps usually indicates a problem. Could be a failed heating element in one of the boots, maybe a wiring issue, a short circuit somewhere. Needs maintenance attention.
And above 32?
Above 32 amps is also bad news. That could suggest a runaway heating element drawing too much current, or perhaps a fault in the timer itself, causing elements to stay on too long or overlap. Again, requires maintenance write-up.
So that de-isometer is really the key indicator for the auto mode.
It is the primary health check, yes.
Now, you mentioned something interesting earlier about the manual mode check. If a pilot selects manual prop de-ice, maybe for troubleshooting or a specific procedure, why does that dedicated de-isometer suddenly read 0? That seems odd.
It does seem counterintuitive at first, but it makes sense when you understand the wiring. In the manual mode, you are intentionally bypassing the automatic timer circuit. And the signal that feeds that primary de-isometer comes from that timer circuit. So if you bypass the timer, you bypass the input to the ammeter. Therefore, it reads 0 amps, even if the elements are drawing power.
Okay, so the gauge isn't broken, it's just not getting the signal in manual mode. What's the operational impact then? How do I confirm the system is actually working if I'm forced to use manual?
This requires an immediate shift in your instrument scan. Since the dedicated de-isometer is now showing 0, you have to look elsewhere for confirmation of electrical load.
Where do you look?
You look at the main aircraft load meters, the gauges showing the total percentage load being drawn from each engine's generator.
Okay.
When you activate the prop de-ice in manual mode, you should see a noticeable increase in the load indicated on both the left and right load meters. The typical value to look for is about a 10% increase per side.
So about 10% jump on the Laird meters confirms the elements are drawing current in manual mode.
Correct. It's a procedural cross-check. It's built into the system. Knowledge requirement, know that the primary ammeter won't work in manual, and know to check the load meters instead. Ensures you always have a way to verify power consumption.
All right, let's move to the front office, keeping the view clear. Cockpit visibility. This area seems unique because we have two completely different systems working side by side.
That's right. You've got electric heating for anti-icing the windshield itself, and then you have the good old mechanical wipers for clearing rain or moisture. Two distinct methods for maintaining visibility.
Let's tackle the heating first. Windshield heat. It's anti-icing, so designed to prevent buildup.
Yes, exactly. This is classic anti-icing. Applying heat to the windshield surface prevents ice crystals or supercooled water droplets from adhering and obscuring vision.
And how does it generate that heat? It's electric, you said.
It is. The King Air windshield is actually a pretty complex structure, typically 3 layers laminated together.
3 layers, what are they?
You usually have an outer glass ply, then a middle layer made of a clear plastic, often polyvinyl butyl or similar. And that middle plastic layer is where the magic happens. It has incredibly fine heating wires, the heating grid, embedded within it.
Ah, so the wires are sandwiched in the middle.
Sandwiched and protected. Then you have the inner glass ply, which provides structural integrity and protects the cockpit occupants.
I remember reading about a Nessa coating on the outside layer, too. What's that about? Is that related to the heating?
Nessa coating usually stands for non-electrostatic application. It's an extremely thin, transparent conductive coating, often indium tin oxide. Its primary job here isn't really heating, but managing static electricity.
Static from rain or snow.
Exactly. Flying through precipitation or even dust can build up a significant static charge on the windshield surface. This Nessa coating helps dissipate that charge evenly, preventing it from building up in one spot, potentially causing radio interference or avionics glitches. It works alongside the heating system, but serves that static discharge role primarily.
Okay. And the pilot has control over the heat intensity.
Yes, independent controls for the pilot side and the co-pilot side. Each has a switch, usually offering 2 settings, normal and HI for high intensity.
When do you use which? Is normal usually enough?
For most icing conditions encountered, normal provides sufficient anti-icing capability. HI delivers significantly more heat and is intended for more severe icing conditions.
Is there a catch to using HI?
There is a limitation, particularly on the ground. You shouldn't use the HI setting for extended periods on the ground, especially if the windshield is already hot from sitting in the sun.
Why not? Risk of damage.
Risk of thermal stress or even cracking. The temperature difference between the superheated inner layers and the outer layer can become too extreme without the cooling effect of airflow in flight. So HI is generally reserved for airborne use in significant icing.
Got it. Now, the pre-flight check for this system involves checking the magnetic compass. That sounds strange. Why does turning on windshield heat mess with the compass?
It's a neat bit of practical physics electromagnetism at work. Those fine wires embedded in the windshield when you push a lot of electrical current through them to generate heat.
And it is a lot of current, right?
Oh yeah, it's a significant electrical load.
Yep.
That current flowing through the grid generates its own magnetic field. And that localized magnetic field generated by the windshield heat is strong enough to interfere with the aircraft's magnetic compass, or, more specifically, the flux gate detector, which is usually mounted relatively close by.
So you actually expect to see the compass swing a bit when you test the heat.
You do. Observing that temporary deflection of the compass needle is actually a required part of the pre-flight check. It serves as an indirect confirmation that the heating elements are drawing the expected high current. If you turn on the heat and the compass doesn't budge, it might suggest the system isn't drawing power correctly.
Clever cross-check. Okay,
Yeah.
Very important topic. Structural integrity. What happens if the windshield cracks? Does it matter which layer?
It matters hugely. The most critical scenario is if the outer ply cracks.
The one facing the elements?
Yes, if that outer glass layer cracks, the aircraft flight manual is explicit. Pressurized flight is prohibited.
Prohibited. Why so strict?
2 main reasons. First, that outer ply is part of the pressure vessel structure. A crack compromises the integrity needed to hold cabin pressure safely. Second, the outer ply protects the heating elements embedded underneath. If it fails, the whole system's airworthiness is compromised.
So if you get an outer ply crack in flight,
Immediate action required. You have to depressurize the aircraft. The procedure involves putting the bleed air valve switches to ENVIR off, environment off, and selecting the cabin press switch to the DMP position. You have to get the aircraft unpressurized and typically divert to the nearest suitable airport for maintenance.
Wow. Okay. What about if the inner ply cracks, the one inside the cockpit?
An inner ply crack is also serious and requires maintenance before the next flight, but it doesn't carry the same immediate catastrophic risk to pressurization as an outer ply failure. The outer structure is still intact. However, it still compromises the overall structural integrity and the environment for the heating element, so it's definitely a no-go item for the next departure.
Okay, good distinction. Let's switch now to the rain removal side. The wipers and washers. These seem more straightforward.
They are relatively conventional, yes. You typically have dual mechanical wiper arms driven by a single electric motor.
Controlled from where?
Usually a switch on the overhead panel or sometimes near the light controls. It typically offers settings like light slow, fast, and park.
Pretty standard. Any key operational points?
The main caution, and it's important, do not operate the windshield wipers on a dry windshield.
Seems obvious, but why stress it?
Because it causes unnecessary wear on the wiper blades, it can easily scratch the windshield surface, especially those specialized coatings like Nessa, and if there's enough friction, you can even potentially burn out the electric wiper motor. Only use them when the glass is wet.
Okay. What about the washer system? How does it get fluid onto the windshield effectively, especially in flight with the wind?
Here's where bleed air makes another appearance. It's quite integrated. The washer system uses engine bleed air again, but this time it's regulated down to a lower pressure, usually around 18 psi.
And what does that bleed air do?
It pressurizes the windshield washer fluid reservoir. That positive pressure is what forces the fluid strongly out of the spray nozzles and onto the windshield, overcoming the aerodynamic forces in flight.
Smart. And how does the pilot activate the wash?
There's usually a push button, often labeled windshield wiper or washer. You press and hold it to spray fluid.
Okay.
But there's a neat little feature here too. When you release that button, a time delay relay kicks in. For about 5 seconds after you release the button, the system continues to push just air bleed air through the delivery lines and nozzles.
A 5-second air purge. Why?
It's an anti-icing feature for the washer system itself. That purge blows out any residual washer fluid left in the lines or nozzles.
Preventing it from freezing and blocking the system for next time.
Exactly. Ensures the nozzles stay clear and ready for the next time you need them, especially if you're operating in freezing conditions where that residual fluid could easily turn to ice. It's a thoughtful piece of engineering.
All right, moving to arguably the most critical area for safety in icing, protecting the engines. The PT-6As in the King Air 350. We've got a couple of systems working here, right?
Yes, 2 main components for engine ice protection. But first, let's establish the operating rule. When must you use the engine anti-ice system?
This sounds like a memory item.
It absolutely is non-negotiable. The rule is engine anti-ice, which primarily means activating the ice vanes, must be on during all ground operations whenever visible moisture is present.
All ground ops in visible moisture. Fog, rain, snow, slush.
Any of it. And then, while airborne, it must be on N whenever you're in visible moisture, and the outside air temperature, the OAT, is plus 5 degrees Celsius or colder.
Plus 5 degrees Celsius or colder in visible moisture in the air. Got it. That's the trigger.
That's the trigger. Clouds, fog, precipitation. If the temp is plus 5 or below, vanes come on.
Okay, so what are the 2 main protective systems? Let's start with the engine inlet lip heat.
Right. This is a passive anti-icing system for the leading edge, the lip, of the engine air inlet cowl. It prevents ice from building up right where the air enters the nacelle.
How does it work? Is it electric? Bleed air?
Neither, actually. It uses engine exhaust heat.
Exhaust heat? How?
There's a small scoop positioned inside the left engine exhaust stack. It captures some of that very hot exhaust gas. This hot air is then ducted through passages built into the structure of the inlet lip, heating it from the inside.
And where does the exhaust go after heating the lip?
It's then vented overboard, usually out the right side of the engine nacelle.
And you said it's passive.
Completely passive. It operates continuously whenever the engine is running. No switches, no pilot action required. As long as the engine is making exhaust, the inlet lip is getting heated. Simple and effective.
Okay, that handles the lip itself. Now, the big one, the ice vanes, also called inertial separators. This is the system that comes with that performance penalty we need to really unpack.
Precisely. The ice vanes are the active part of the system, the part the pilot turns on based on that plus 5 degree rule. Their function is inertial separation.
Meaning?
Meaning They're designed to separate heavier particles like water droplets, ice crystals, snow, or even things like sand or gravel on the ground from the lighter air that the engine needs. They prevent these heavier particles from making the sharp turn required to enter the engine's compressor inlet.
Okay, let's visualize this. Describe the vanes when the system is OFF in normal flight.
In the normal anti-ice OFF configuration, there's usually a forward vane that is positioned UP or retracted, is essentially flush with the upper inlet duct. And there's an aft vane, which is positioned down in N.
What does that configuration achieve?
It creates the smoothest, most direct path for ram air to flow straight into the engine intake plenum. Maximizes airflow, maximizes ram pressure recovery, gives you the best engine efficiency.
Okay, smooth flow for normal aux. Now, what happens physically when I select engine anti-ice on it?
When you select on-N, an electrically operated linear actuator moves both vanes simultaneously. The forward vane lowers down into the airstream pass. At the same time, the aft vane retracts or moves upward.
Forward vane down, aft vane up. And this actuator is just on or OF, right? No in between.
Correct. It's a binary system. The actuator drives the vanes fully to the deployed on-N position or fully to the retracted OFF position. There are no intermediate settings.
So how does that new vane position, forward one down, aft one up, actually protect the engine from ice?
By lowering that forward vane into the main airflow path, you force the incoming air to make a very sharp, abrupt turn downwards to get around it and then upwards again towards the engine plenum.
Okay, a sharp detour.
A very sharp detour. Now, the relatively light air molecules can make that turn, but heavier particles, water droplets, ice crystals, snow, have too much inertia. They can't make the sharp turn.
They just keep going straight.
They essentially keep going straight and are ejected overboard, usually through a bypass duct or opening in the lower part of the engine nacelle. You're literally separating the heavy, potentially damaging stuff from the clean air the engine needs.
So you're intentionally disrupting the airflow to clean it.
You are intentionally sacrificing some airflow efficiency and ram recovery in exchange for protecting the engine compressor blades from ice or foreign object damage. It's a safety trade-off.
Okay. And the indication in the cockpit that this has happened successfully.
You'll get the LENG anti-ice and RENG anti-ice enunciator lights illuminating. Those lights confirm the vanes are in the deployed or anti-ice on-N position.
Right. But this is where the operational consequence, the performance hit, comes in. We absolutely have to detail this. What happens to engine performance when you turn the anti-ice on, assuming for a moment there's no actual ice accretion yet? Just the act of deploying the vanes?
This is core systems knowledge for any King Air pilot. Deploying those vanes does several things. It creates turbulence in the inlet, it lowers the ram pressure recovery, and it ultimately reduces the mass of air entering the engine compressor.
And the measurable effect on the gauges.
The direct, immediate result you will see is a decrease in engine torque. Specifically, torque will drop by approximately 14 percentage units.
14%. Just by flipping the switch, that's substantial.
It is a very significant reduction in available power.
So what happens if a pilot deploys the vanes, sees the lights come on, but doesn't immediately adjust the power levers? They just leave them where they were?
If you don't compensate, the aircraft's performance will drop noticeably. Because the engine is now producing 14% less torque for the same power lever setting, your true airspeed, TAS, will decrease by about 20 knots.
20 knots slower.
Approximately, yes. And interestingly, because the engine is now less efficient in processing less air mass, your fuel flow will actually decrease slightly as well, by about 40 pounds per hour per engine. But the main hit is the loss of speed and power.
Okay. But the standard procedure, the proficient pilot's action, is to immediately compensate for that torque loss, right?
Absolutely. As soon as those anti-ice lights illuminate, your hand should be going to the power levers to bring the torque back up to your target setting, whether that's maximum continuous, max cruise, or whatever the phase of flight requires.
So if I immediately reset the torque back to where it was before I turn the anti-ice on, what happens to speed and fuel flow then?
If you follow the book and reset to the desired handbook power setting, for example, maintain the same target torque, then you will successfully mitigate the speed loss. Your true airspeed should remain more or less unchanged.
Okay, so I keep my speed, but there's no free lunch, right?
No free lunch. You've maintained your speed,
Right.
but you're now forcing the engine to produce that original level of power with less efficient turbulent air entering the compressor. To do that, the engine has to burn more fuel.
How much more?
Fuel flow will increase by approximately 45 pounds per hour per engine, compared to having the anti-ice OFF at that same power setting.
So anti-ice on N, power reset, same speed, but burning about 90 pounds per hour more total fuel.
That's the trade-off. You maintain performance, but you sacrifice fuel efficiency and endurance for the safety margin provided by the ice vanes.
Okay, that's crystal clear. Now let's link this back to that takeoff limitation we
Yeah.
said. Ambient temps above plus 10 degrees C, engine anti-ice must be O off F for takeoff. Why plus 10? Why not the plus 5 rule we use in flight?
The reasoning is risk versus penalty. Above plus 10 degrees Celsius, even if there's visible moisture like rain, the risk of significant engine induction icing during the short takeoff roll and initial climb is considered extremely low, negligible really.
Okay.
So if you were to turn the anti-ice on unnecessarily in those warmer conditions, you'd be imposing that mandatory 14% torque penalty right at the start of your takeoff roll.
Which could compromise takeoff performance, especially at high weights or high density altitudes.
Exactly. You'd be reducing your available power for no significant safety gain in those conditions. The AFM mandates using maximum available performance when it's safe to do so. Hence, the plus 10-degree cutoff for takeoff.
Makes sense. And one final, absolutely critical number related to performance planning with engine anti-ice. The 1,400 feet penalty. Explain that.
Right. This is crucial for accurate performance calculations using the charts in the AFM. The manual recognizes that deploying the ice vanes fundamentally changes how the engine breathes. It reduces the density and efficiency of the air reaching the compressor.
It's like the engine thinks it's at a higher altitude.
That's exactly the analogy the AFM uses for calculation purposes. To accurately predict your takeoff distance, climb gradient, or cruise performance when you plan to use engine anti-ice, or are required to use it, you must artificially increase your pressure altitude by 1,400 feet before entering the performance charts.
So if I'm taking off from an airport at 5,000 feet pressure altitude, but I need engine anti-ice on in, I calculate my performance as if I were at 6,400 feet.
Precisely. That 1,400-foot adjustment is the book's way of quantifying, of putting a number on, the aerodynamic drag and engine efficiency penalty imposed by having those vanes deployed. It ensures your performance predictions remain conservative and safe when using the system. It's not just a switch, it changes the numbers.
Okay, we've covered the big surfaces and the engines. Now let's talk about the smaller but equally vital systems. The probe and sensor anti-ice. Easy to overlook, maybe, but critical.
Absolutely critical. You lose reliable flight information. We're talking about systems that provide heating for things like the pitot tubes, the stall warning vane, fuel vents.
All electrically heated.
Generally, yes. These are typically electrothermal systems. Their failure can lead directly to incorrect airspeed indications, unreliable altitude, faulty stall warnings, potentially catastrophic failures.
Let's start with the pitot tubes. Standard component, but the heating is key.
Yes, you have independent pitot tubes for the pilot and co-pilot side, providing ram air pressure for the airspeed indicators. Both are electrically heated.
Pilot action.
Two things are mandatory. First, on pre-flight, absolutely ensure the pitot tube covers are removed. Sounds basic, but it's missed. Second, the pitot heat switch must be selected on for flight.
Okay. Now, there's sometimes an annunciator light associated with pitot heat, but it works backwards.
That's right. If the optional L or R PITOT heat annunciator lights are installed. Unlike most system lights that come on to show activation, these lights actually extinguish when you select the pitot heat switch on and the system is working correctly.
So the light being on means the heat is over F or failed.
Exactly. The annunciator illuminates to indicate a failure condition. No current draw. When you turn the heat on and the element draws current properly, the failure condition is cleared and the light goes AUT.
So light out is good. It's an effective check that the element has continuity and is drawing power.
Precisely. A bit counterintuitive, but it works as a status check.
Okay. What about the fuel system? Why do fuel vents need heating? That seems less obvious than pitot tubes.
It's crucial for preventing fuel starvation or tank damage. The fuel tanks need to be vented to the atmosphere to allow air to replace the fuel being consumed by the engines.
Right, prevents a vacuum forming in the tank.
Exactly. These vents, usually located on the underside of the wing or near the wing tips, can become blocked by ice crystals or frozen moisture in icing conditions.
And if the vent blocks?
If the vent gets blocked as the engines draw fuel out, a negative pressure, a vacuum, builds up inside the tank. This can either prevent fuel from flowing out to the engines, leading to fuel starvation and engine flameout, or, in extreme cases, the pressure differential between the inside and outside of the tank can become so great it can actually cause structural damage, collapsing the tank walls inward.
Wow. Okay, so heated fuel vents are critical. Are they always on?
Typically, the fuel vent heat is activated along with the main pitot heat switch, ensuring they're protected whenever pitot heat is needed.
Got it. And the last key sensor. The stall warning vane, sometimes called the lift transducer, also heated.
Yes, very important. The stall warning system relies on a small, movable vane mounted on the wing's leading edge to measure the angle of attack of the airflow. This vane and its mounting plate, the faceplate, are both equipped with electrical anti-icing elements.
Powered from where?
It's usually powered from the right generator bus, according to the manuals.
Now, this one has some interesting logic tied to the landing gear, doesn't it?
It does. The heating level for the stall warning vane is automatically adjusted based on whether the aircraft is on the ground or in the air.
How does it know?
It uses input from the landing gear safety switch, or squat switch, typically the one on the left main gear.
Okay, so what's the logic?
The stall vane heat must be turned on for all flights. That's step one. When the aircraft is on the ground, weight on wheels, the squat switch tells the system, we're on the ground. The system then applies a reduced level of heat to the vane and faceplate.
Why reduced heat on the ground?
To prevent the heating element from overheating. There's much less cooling airflow over the vane when parked or taxiing compared to flight. Reduced heat protects the element and also saves a bit on electrical load.
Makes sense. And when you take off?
As soon as the gear lifts off the runway, the squat switch signals weight off wheels. The system then automatically switches to applying the full level of heat to the stall vane.
Giving it maximum anti-icing capability for flight conditions.
Correct. Ensures it's adequately protected against ice accretion at altitude and higher airspeeds.
Now, a crucial reminder here. Even though the vane itself is heated, structural ice on the wing around the vane can still cause major problems, right?
This is absolutely critical to understand. The heated vane itself might remain ice-free. But if the wing leading edge ahead of the vane accumulates ice, that ice changes the shape of the airfoil.
Which changes how the air flows over the vane.
Exactly.
Yeah.
The altered airflow due to structural ice can cause the wing to stall at a significantly higher airspeed or a lower angle of attack than what the stall warning system is calibrated for in clean conditions.
So the stall horn might go off too late, or maybe not at all, before the actual aerodynamic stall occurs.
That's the danger.
Mm.
Relying solely on the stall warning horn or stick shaker when you know you have ice accumulated on the airframe is extremely hazardous. The actual stall speed is increased by the ice, potentially significantly, and the warning system may no longer be accurate. You need to maintain a higher airspeed margin.
Okay, we've dissected the individual systems. Let's pull it all together now by focusing on the really critical operating limitations from the flight manual and what you absolutely need to check during your pre-flight walk-around regarding these systems.
It's a good plan. These are the hard rules and the hands-on checks.
Let's start with what you'd consider the single most critical, absolutely non-negotiable limitation when dealing with structural icing.
Without a doubt, the one limitation that must be burned into every King Air pilot's brain is this. Flight in known or forecast icing conditions with the wing flaps extended is strictly prohibited.
Prohibited. Not avoid, not use caution. Prohibited. Full stop.
Full stop. The aircraft must be operated in the clean configuration, flaps UP, whenever you are in icing conditions.
Why is that rule so absolute? What's the danger with extending flaps in ice?
Several severe dangers. Firstly, when you extend flaps, you expose parts of the wing trailing edge and the flap mechanism itself, areas that are not protected by the de-ice boots on the leading edge.
Okay.
Ice can accumulate rapidly on these unprotected flap surfaces and hinges. This buildup does two very bad things. It drastically changes the aerodynamic characteristics of the wing, increasing drag and significantly altering stall behavior in unpredictable ways.
Leading to potential loss of control.
Yes. And secondly, the ice accumulation can physically jam the flap tracks or mechanisms. You might extend the flaps and then find you cannot retract them because they're frozen in place. Or worse, asymmetric jamming could occur.
Meaning one side retracts and the other doesn't?
Leading to an immediate, severe roll control problem. The bottom line is, the aircraft's certified performance and handling characteristics in icing conditions are only valid for the clean configuration. Extending flaps takes you outside that certified envelope.
Okay. Prohibition on flaps in icing. Crystal clear. Let's quickly recap the temperature limits we touched on.
Right, two key ones. For the pneumatic de-ice boots on the airframe, do not operate them if the OAT is below minus 40 degrees Celsius or Fahrenheit. Risk of boot damage.
Minus 40 limit for boots.
And then there's the overall minimum operating air temperature limit for the entire aircraft, which is stated in the AFM. For the 350, that's typically minus 53.9 degrees Celsius.
Minus 53.9 C. That's incredibly cold.
It is. Operating near that absolute limit raises concerns about the structural integrity of various components, fluid viscosity, and overall system performance. It's the certified cold boundary for the airframe.
Okay, now let's walk around the aircraft. Pre-flight inspection. What specific items related to ice and rain protection must a pilot check every single time?
This is part of your standard flow, but needs focus. First, absolutely verify all pitot tube covers, static port covers, and stall warning vane covers are removed. Mandatory checklist item, easy to miss, disastrous if forgotten.
Especially with heated probes. Could damage them on the ground if left covered.
Could indeed. Second, look at the engine ice vanes inside the nacelle inlets. For pre-flight, they should be in the retracted or normal OFF position. Ensure they're flush.
Check. What about the propellers?
Detailed inspection here. Check the blades themselves for security, any signs of nicks, cracks, or damage. Look for any signs of fluid leakage, like oil from the hub area, and then specifically inspect the propeller de-ice boots. Check their condition, look for tears, peeling edges, signs of wear or delamination.
Okay, moving to the airframe boots.
General condition check of the wing and tail de-ice boots. Look for obvious damage, like rips, tears, or loose patches. Ensure they look properly seated against the leading edge.
Windshield.
Inspect the windshield carefully. Look for any signs of delamination between the layers, cloudy spots, or bubbles, and specifically check that outer ply for any cracks, however small. Remember, outer ply crack means no pressurized flight.
Right. And finally, often overlooked, but vital for instruments.
The static ports. Locate them, usually small holes on the sides of the rear fuselage, both left and right. Ensure they are completely clear, free of obstructions like mud, insects, ice, or even tape left over from washing or painting.
Because a blocked static port gives you
Completely unreliable airspeed, altitude, and vertical speed information. One of the fastest ways to get into serious trouble, especially in instrument conditions. Check those ports diligently. #conclusion and review.
Okay, this has been a really thorough deep dive. We've broken down a complex suite of systems. Let's try to offer a final, concise summary, maybe framing it around those two different philosophies you mentioned earlier.
Yeah, that's a good way to think about it. Broadly, we have two strategies at play on the King Air 350 for dealing with ice. First, there are the anti-icing systems. These are proactive. Their job is to prevent ice from forming or adhering in the first place.
What falls into that category?
That includes the engine ice vanes when deployed, the heating for the pitot tubes, fuel vents and stall warning sensor, the electric windshield heat, and that continuously operating engine inlet lip heat using exhaust. Preventative measures.
Okay. And the second philosophy?
That's de-icing. These systems are reactive. They're designed to remove ice after it has already accumulated to a certain point.
And that's primarily?
That's primarily the pneumatic D's boots on the wings and tail. The system that requires you to wait for that ½ inch to an inch of buildup before cycling.
So anti-icing prevents, de-icing removes. Both require the pilot to be actively involved, monitoring, and making decisions.
Absolutely. Neither system is fully fire and forget. They demand understanding, monitoring, and timely activation or management.
Right. To help really cement this knowledge, let's pose that practical scenario question directly to you, our listener. Imagine this. You're in cruise flight, at flight level 210. The outside air temperature is reading -10 degrees Celsius. You look ahead and see you're about to enter a layer of visible moisture, maybe some light clouds.
Okay, FL 210, -10 degrees C, entering clouds.
What is your immediate action flow for activating the necessary ice protection systems? And critically, what change in engine performance must you instantly anticipate and compensate for?
Okay, thinking through the rules.
Okay.
OAT is -10 degrees C, which is definitely below the +5 degree C threshold. And you're about to enter visible moisture.
Yep.
So the immediate actions. Engine anti-ice switches must come on. Deploy those ice vanes.
Okay, vanes on in. What else?
You'd also need to ensure the windshield anti-ice is operating, likely selecting it to the normal heat setting as part of your standard flow for entering icing conditions if it wasn't already on from the climb checklist.
Yeah.
Prop heat should also be on in auto.
Engine anti-ice on, windshield heat normal, crop heat auto. Got it. Now, the crucial part. The immediate required compensation.
The absolute key action, tied directly to selecting engine anti-ice on N, is anticipating that immediate drop in engine torque. You know it's coming approximately 14 percentage units.
So what do you do?
Your hand goes straight to the power levers. As those LRENG anti-ice lights illuminate, you smoothly advance the power levers to bring the torque right back up to your target cruise setting.
Why is that immediate compensation so important?
To prevent that roughly 20-knot loss in true airspeed that would otherwise occur, Maintaining your planned cruise speed is vital for performance, fuel planning, and maintaining an adequate margin above stall speed, especially now that you're in icing conditions where stall speed naturally increases. You actively manage the engine to counter the safety system's inherent penalty.
That interaction activating a safety system, which then requires immediate pilot input to counteract its performance penalty, that really is the essence of proficient turboprop flying, isn't it?
It absolutely is. It's not passive automation. It's active management of the aircraft's energy state, its aerodynamics, its thermodynamics, all in response to changing environmental conditions and system activations.
Well said. And that brings us to our final, maybe provocative thought for you to consider.
We talked a lot about that 14% torque penalty, the speed loss or fuel burn increase. But maybe the ultimate distillation of understanding this system's impact is found right there in the performance section of the AFM.
That 1,400-foot adjustment.
That 1,400-foot pressure altitude adjustment required for performance calculations when engine anti-ice is on N. Think about what that number represents. It's not arbitrary. It is the flight manual's quantified assessment of the aerodynamic and thermodynamic cost of using that essential safety system.
It tells you the system fundamentally changes how the aircraft performs.
Exactly. It serves as a constant reminder that these ice protection systems, while absolutely critical for safety, aren't free. They change the aircraft's performance envelope, and the ultimate skill is not just knowing which switch to flip, but recognizing when flipping that switch demands you also adjust your performance expectations and calculations. You have to think like a pilot and a bit like a performance engineer simultaneously.
Essential knowledge, complex interactions, hopefully now synthesized for your understanding and retention. That concludes our deep dive into the King Air 350 ice and rain protection systems.
Fly safe and stay ahead of the ice.